Alright, and welcome back to the summary video. Again, remember, if you have not done all these problems already, go back and do them again, and then watch this just to summarize, because it won't make as much sense if you haven't done them already and you're just trying to listen. So, go back, look at it, at least try it, and then come back here. So, we're going to start with 5-26, where we're actually going to try using our inverse trig functions, at least for a couple of these. C, we're solving for a side length, but for A and B, we're both solving for theta. I'm going to walk you through the steps for A and B here at least, and show you how to get theta for them, how to set it up, how to walk through those steps, okay? As you can see here from my lovely handwriting that I've been doing on my phone, we set up our triangle exactly as it is in the diagram, and you can see that I've already labeled it exactly the same way I would for any one of our triangles that we've been doing so far. I put the O, H, and A there so I can determine what's the opposite, what's the adjacent, and which one's the hypotenuse. So, for this one, I've got that 12 and 24. 12 is adjacent to theta, 24 is the hypotenuse, so if I look at my SOHCAHTOA there, I'm using cosine. So I set this up exactly the same way I would otherwise. Cosine of theta equals 12 over 24. Again, the only difference here in the setup is what I'm putting where. It's just that my variable ends up in the angle spot. So, I want to get theta by itself. In order to do that, I've got to get rid of whatever's next to it. So, I'm cosining theta, so I've got to uncosine theta. So I've got to do the opposite. So I've got to do the inverse cosine of both sides. I get the inverse cosine of the cosine of theta equals the inverse cosine of 12 over 24. That inverse cosine and cosine cancels out, leaving me with just leaving me with just theta on the left side of the equation equal to the inverse cosine of 12 over 24. Remember, this is a perfectly acceptable answer by itself already, but if we can put that into a calculator, it should give us exactly 60 degrees. So that's how you solve part A. Alright, that brings us to part B here, which, if you remember our slope ratios from earlier in chapter 4, you may be able to do this one without any work, but I'm just going to assume that we don't, and I'm going to do this one the long way. But if you remember it, this would be much quicker. Alright, so first step, label the sides, O, H, and A. I can see that I've got the opposite side and the adjacent here with my two 8s. Looking at my SOHCAHTOA, O and A are the only ones present in tangent with T, so I'm using tangent. Start with my setup. You'll notice my first step is exactly the same every single time for any type of trigonometry problem. Consistency. So, I start with tangent of theta equals 8 over 8. I gotta get rid of that tangent, I gotta get theta by itself, so I take the inverse tangent of both sides. I get the inverse tangent of theta equals the inverse tangent of 8 over 8. Inverse tangent of tangent cancels out, and I get theta equals the inverse tangent of 8 over 8. Putting this into my calculator, I get theta equals 45 degrees. Now, if you remembered that 8 over 8 is 1, and the slope ratio for 1 is 45 degrees, you may have been able to do that a little quicker. And if you just looked at this and noticed that the two sides were equal to each other, you may have just been able to jump right to that being 45 degrees. But in case you couldn't, we went through this long process anyway, just to show you. And now, because I know you've missed weird anecdotes from being in my actual class and me going off on tangents and stuff, I installed one into this video. So, what you're looking at here is the staircase in my mom's house back in Illinois. Now, this is one of those times when, you ask me, when are we ever going to use this in real life? Here is a time I literally used this in real life a couple of years ago. I was still teaching at the time, this class. So, not your class, a different class, previous year. And it was over winter break, and I was home, and I used this, and I was so excited, because I was like, oh my god, I just used trigonometry. I can bring this back and show this to my students. Hence why there's a picture. So, basically, what you can see that little piece of wood on the wall there, that white piece of wood that kind of comes in at an angle and meets up with the staircase. Well, my mom was installing baseboard molding in her house, which is that little piece of board on the bottom that protects the bottom of the wall and covers up the seam between the floor and the wall. So she was installing that in her house, and I was home and I was helping her out. And generally it's pretty easy. You just measure it, cut it, and then just, attach it onto the wall. But we got to this point where we needed to put it right up underneath the staircase. And you'll notice that it comes in at an angle. Well, saws you can set at a specific angle, literally 2 degrees. Like, it's basically got a giant protractor on the bottom of it. And you can set it to a specific angle and cut to that angle very accurately. So we needed to figure out what angle we needed to cut at. Well, I don't know how well you can see it if you look really close on your screen, but the corner of that, or the edge of that staircase piece of wood there is a little banged up, dinged up, not exactly a straight line. Some people could blame the cat from scratching it up. Some people could blame a teenage math teacher for running into it too many times with a vacuum cleaner. Who knows who's to blame? But all I know is that it's really hard to get an exact reading of that with like a protractor or something. So it's in fact much easier instead to measure the height and base, or the change in y, change in x, of that line, basically figure out its slope in lengths, and then apply inverse tangent and figure out exactly what that angle should be, which is what I did. I took a tape measure, I measured over, and then from that exact point I measured up, and I figured out the slope of that line, used inverse tangent to figure out what the angle should be, put that angle into the circular saw, cut it, and look at it. It fits perfectly. So that's an application of trigonometry in real life. And in fact, it wasn't just like one weird time because I'm a geometry teacher that I've done this. Back when I used to work in construction, in doing set construction for theater, I used trigonometry all the time. It was one of the most it's where I actually got really good at doing it quickly, is because I would have to do like calculations on 2x4s to figure out what angle I need to set a saw at, or how long something should be in order to achieve a certain angle. If you're going to build something and you want it to be a specific size, specific angle, specific length, you need to use trigonometry in order to figure out what those things should be. So this is one of the most applicable areas of math because it's used constantly in things like construction and design. All right, and last but not least, we can see here Peter, who has basically, he's set up his equation. He's got cosine of theta equals 8 over 2.736. He's trying to figure out what happened because he puts this into a calculator and the calculator just gives him error. And if you put this into your calculator, you will get an error. Now, some of you might immediately jump to, oh, he doesn't have parentheses around theta. While you're correct, that's not the problem. If you put something like this in your calculator, you will get an error. And very frequently, I will have people on tests who will be like, my calculator is broken. It's giving me an error because I put this in and it won't give me an answer. That doesn't mean your calculator is broken. This won't give you an answer for a very good reason. I'm going to give you a minute. If you haven't already taken a look at this, haven't already considered it, take a second, pause the video right now, really think about it. What about this might give you an error? What might be wrong with this if you try to do inverse cosine of 8 over 2.736? Go ahead and pause now. All right, welcome back. So, I'll give you a hint if you haven't figured it out yet. It has to do with what side length goes in what part of that fraction. Okay, so if you still don't have it, or if you're waiting for me to tell you the answer, if we think about it, the numerator, cosine, so katoa, cosine is adjacent over hypotenuse, right? Well, if you look at that, the length of the adjacent side is 8, the length of the hypotenuse is 2.736. That is that's not possible for a right triangle. The hypotenuse is always the longest side of a right triangle, and in this fraction, it's saying the adjacent side is like 5 or 6 longer than the hypotenuse, which doesn't make any sense. That can't form a right triangle. So if you put this in a calculator, it'll give you an error because what you're trying to tell it is an impossible shape. So keep that in mind. Always make sure you're setting this up correctly, and always keep in mind that when you're using sine or cosine, your denominator always has to be bigger. Tangent, not the case. All right. Hopefully this has been helpful. Again, if you have any questions, if things aren't making sense, drop in the Google Meet call or send me an email and I will happily check in on you. I also posted yesterday that you have an assignment due tomorrow, just whatever your notes are for Chapter 4, so 411 through 415. This should already be stuff you did last week. Just take pictures of it and post it in Google Classroom just so I can make sure you're taking your notes and I can check in and make sure you're staying on task and doing your work. All right, so until next week. Oh, no, actually, you're going on spring break. So until like 2 weeks from now, have a lovely spring break, and I will talk to you all when you get back.